It feels like we're constantly hearing about large language models, LLMs, right?
Yeah.
And how they're getting smarter, but also, well, how much stuff they need to process. It's like trying to drink from a fire hose sometimes.
It really is. The amount of data they churn through is staggering.
Yeah.
And honestly, we're starting to hit some real bottlenecks with the current ways we build AI.
That feeling of information overload. It's not just us, huh? Even the AI is feeling it.
Exactly.
Welcome, everyone, to The Deep Dive. We're your shortcut to understanding what's next. And today, wow, we've got something really interesting, spiking brain.
Yeah, this isn't just a minor tweak. It's a whole new approach,
Right.
really inspired directly by, well, how our own brains work.
Brain-inspired AI. Okay, so our mission today, break down spiking brain. What is it? What big problems is it trying to fix with current AI models?
And crucially, how does it work differently? Because it's quite a shift from the LLMs everyone talks about, like the transformer models.
Right. And we'll get into what this could mean for AI hardware, software, maybe even some big tech companies, Our goal is to give you the essentials, some cool facts, clear explanations so you can really get a handle on this.
Sound good.
Let's do it. Okay, so let's set the scene. These current LLMs, mostly built on that transformer architecture, they're amazing, no doubt. They write, code, translate.
Incredibly powerful. But, and it's a big but,
Yeah.
they come with some serious baggage, some real challenges that are becoming bottlenecks.
Like what? What are the main headaches?
Well, first, the cost is just astronomical. Training these things needs unbelievable amounts of computing power and energy. We're talking data centers guzzling energy. It's a lot.
Okay, cost. What else?
Second, they really struggle with long sequences of information. Think trying to understand a whole book or a really long meeting transcript. For current LLMs, the computation needed to train on that scales quadratically.
Quadratically meaning?
Meaning if you double the length of the text, the work needed goes up 4 times, it gets out of hand fast, and even just using the model inference, the memory it needs grows linearly.
Yeah.
So long context is a major pain point.
Gotcha. Costly and not great with long reads. Anything else?
Yeah, third point, getting these models to train and run well, stably, efficiently, on anything other than NVIDIA hardware. That's a huge challenge. NVIDIA really dominates the AI chip market right now.
Okay, so dependency on one type of hardware is also a bottleneck.
Absolutely.
Yeah.
And what's fascinating here, is why these issues exist. It links back to this idea of scaling law. Basically, the thinking has been more data, bigger model, better result.
Which worked up to a point.
Exactly. It worked. But the costs, financial, energy, computational, are just hitting a ceiling. We can't just keep throwing more and more power at it forever. It's not sustainable.
So we need a smarter way.
Precisely. And that's why people are looking seriously at the human brain. It's incredibly powerful and incredibly energy efficient, right? It manages complex tasks with limited resources. The question is, can we learn from that?
And that brings us right back to spiking brain. You said it's a new family of brain-inspired models. So how does this brain-inspired idea actually, work? How is it different?
Okay, so the core concept is a really fundamental shift. Traditional LLMs process data, kind of like a continuous stream, always calculating. Spiking brain uses spikes.
Spikes, like Morse code.
Sort of. Think about how neurons in your brain communicate. They don't just constantly buzz, they send out a discrete signal, a spike. Only when there's something important to signal, an event. They're quiet otherwise.
Okay.
But the key here for computing is that it's not just about sending the signal. The computation itself becomes event-driven. Operations only happen when a spike occurs. Imagine that versus a system that's constantly crunching numbers, even when nothing much is changing.
Right, so instead of a constant hum of activity, it's bursts of calculation only when needed. That sounds way more efficient.
Exactly. That's the core idea that leads to potentially massive energy savings.
So connecting this to the bigger picture, that event-driven thing, that's the main difference from the usual transformer models.
Yes, fundamentally. Let's try an analogy. Think of a standard LLM like a water tap that's always running. Water's flowing, energy's being used, whether you're filling a cup or not, it's always processing.
Okay.
Spiking brain is more like one of those motion-activated faucets or maybe a water fountain you press a button for. It only activates and uses water, or in this case, computation when there's an actual need, an event.
I like that. Only compute when you press the button. That makes intuitive sense for efficiency. What does this mean for performance and, the data needed?
Well, the performance is actually really promising. The researchers found spiking brain models can achieve results comparable to open-source transformer baselines, so similar quality.
Okay, comparable performance,
Right.
but the efficiency payoff.
is huge,
Yeah.
especially the data resources. They mention needing only around 150 billion tokens for what they call continual pre-training. Compare that to the roughly 10 trillion tokens often used to train big models from scratch.
Wait, 150 billion versus 10 trillion? That's
Less than 2%, yeah. Think about what that means. It potentially blows the doors open for who can develop cutting-edge AI.
Mm.
You might not need the resources of a tech giant anymore. Smaller teams, startups,
yeah.
it could really democratize things.
Wow, okay. Less than 2% of the data. That's a game changer right there.
Yeah.
But how? How does Spiking Brain actually pull this off? What are the technical tricks under the hood?
Right. It boils down to basically three key innovations they talk about.
Bam on us.
Okay, first, the model architecture. They moved away from the standard softmax attention used in transformers. That's the part that gets really computationally heavy, especially with long sequences, that quadratic scaling we mentioned.
Right, the bottleneck.
Exactly. So Spiking Brain uses hybrid linear attention. It's a mix of clever ideas. There's sliding window attention, or SWA, that focuses just on the nearby context, like looking at words immediately around the one you're reading. Much cheaper computationally.
So, local focus. What else?
Then there's linear attention. This is cool. It's designed to compress the important bits from really long sequences into a small, constantly updated memory. Kind of like how you remember the gist of a long book without recalling every sentence. Great for long-range understanding without the quadratic cost.
Okay, local and long range, but efficiently.
Precisely. And the third part of the architecture is mixture of experts, or MOE. This lets them make the model bigger, give it more capacity, but without making every computation heavier.
How does that work?
Imagine you have a team of specialists. Instead of asking every specialist about every single problem, you only call on the one or two experts most relevant to that specific problem. MOE does that inside the model only activates a small subset of expert parameters for each piece of data.
Ah, like routing the work to the right specialist. Is that also brain-inspired?
Very much so. Linear attention has parallels to how dendrites in neurons integrate signals over time. And MOE is like how different parts of our brain specialize in different tasks. Modularity, right? Rather than one big homogeneous blob trying to do everything.
Okay, that architecture makes sense. Hybrid linear attention with MOE. What's the second innovation?
The second one is adaptive threshold spiking. This is really where the spiking name comes alive. It's about converting the model's internal signals, which are usually continuous numbers, into integer spike counts and then into sparse spike trains.
Okay, talk me through that, like the neuron analogy.
Exactly like the neuron analogy. Think of a neuron's internal energy, its membrane potential. It only fires, sends a spike, when that potential crosses a certain threshold.
Right.
But here's the adaptive part. That threshold isn't fixed. It can adjust itself based on how active the neuron has been recently. If it's been firing a lot, the threshold might go up to calm it down. If it's been quiet, it might lower to become more sensitive.
Ah, so it regulates itself to stay efficient, prevents it going haywire or completely silent.
You got it. It keeps things balanced and sparse. And this directly enables that event-driven computation calculations only happen when a spike actually occurs. No spike, no compute for that part.
Super efficient. Okay, architecture, adaptive spiking. What's the third key?
The third is just looking at the efficiency metrics they achieved. The numbers are pretty striking. They report achieving 69.15% sparsity.
Meaning over 2/3 of the model is essentially inactive or quiet at any given moment.
On average, yes. That directly translates to power savings. And the energy reduction numbers are dramatic. They claim a reduction of 97.7% compared with FP16 that's standard 16-bit floating point math, and 85.2% compared with INT8 max, which is 8-bit integer math, already more efficient.
Wait, 97% reduction, that's huge.
It is. It translates to potentially 43.48 times energy efficiency improvement over FP16 and 6.76 times over INT8. It's a massive leap in doing more with less power.
So, like you said, not just an incremental improvement. This combination of MOE sparsity and the neuron-level spiking sparsity seems really powerful. Does this open up things that were just, well, pipe dreams before?
It certainly points in that direction. And this raises an important question about hardware. This kind of efficiency is perfect for what's called next-generation neuromorphic hardware.
Neuromorphic, meaning brain-like chips.
Essentially, yes. Chips designed from the ground up for this kind of event-driven spiking computation. Imagine hardware that's inherently low power because large parts of it are literally doing nothing until a spike arrives. That could enable AI in places we can't currently put it, Tiny sensors, wearables, devices running on batteries for ages.
That sounds like a whole new category of AI
It
applications.
could be. It's not just making current AI cheaper, it's potentially enabling totally new forms.
Now, speaking of hardware, you mentioned earlier that one of the bottlenecks for current LLMs is the reliance on NVIDIA, but spiking brain, this was developed somewhere else.
That's right. The paper explicitly states it was developed and trained on the MEDIC-X GPU cluster, which they identify as a non-NVIDIA computing platform.
Okay, why is the detail such a big deal? Seems technical, but sounds important.
Oh, it's strategically huge. Because as we said, NVIDIA has had such a stranglehold on the high-end AI training market. Successfully developing a cutting-edge model like this on an alternative platform demonstrates that it is feasible.
So it fosters AI software and hardware independence.
Exactly. It proves large-scale LLM development can happen outside the dominant ecosystem. That encourages competition, reduces the risk of relying on a single vendor, and could lead to a more diverse, maybe even more innovative hardware landscape.
What about the impact on, say, US tech companies, both software and hardware? Does this threaten the established players or open doors?
It's probably a bit of both, or maybe it just reshapes the opportunities. If spiking brain or similar approaches really take off, yes, it could challenge existing market shares built on older architectures, but it also creates massive opportunities for companies, including US ones building new hardware optimized for this, or software tools, or entirely new AI applications enabled by this efficiency. Think about it. If AI gets way cheaper and more efficient, the total market for AI could grow enormously, benefiting lots of players.
So it's not necessarily a zero-sum game. New efficiency could unlock new demand.
Precisely. But, and this is really important to stress, we need a crucial warning here. While these results from the paper are incredibly exciting, very promising, they need to be confirmed. We need broader research, independent verification, and see how it performs when adopted more widely in the industry.
Right. It's still early days. This is one research paper, albeit a compelling one.
Exactly. It's a frontier, a very promising one, but still a frontier. We need to see how it scales, how robust it is in different scenarios.
That makes sense. So what are the biggest practical hurdles you see for spiking brain moving from, cool research paper to industry standard?
Well, ecosystem's a big one. NVIDIA didn't just build chips. They built CDA, libraries, frameworks, a whole environment developers rely on. For spiking brain or neuromorphic approaches to thrive, you need that same level of robust tooling and support on the alternative platforms.
So the software side needs to catch up to the hardware potential.
Definitely. And also just scaling and testing. The benchmarks look great, but proving this works reliably for massive, complex, enterprise-level tasks across diverse industries, that takes time and a lot more work.
Okay, noted. But let's circle back to some of those impressive results they did report. You mentioned performance comparable to baselines, but were there specific speedups?
Yes, some really eye-catching ones. For inference, using the model their Spiking Brain 7B model got more than 100x speed up in time to first token, TTFT, for 4M token sequences.
100 times faster to get the first response on a really long input. That's huge for interactive use.
It really is. That initial delay can be frustrating. And it's not just for giant servers. They took a smaller, compressed 1 billion parameter Spiking Brain model and ran it on a standard CPU.
Like in a regular computer.
Yeah, exactly. And even there, compared to a similar-sized standard model, Llama 3.21b, it achieved a 15.39x speedup when processing sequences of 256,000 tokens.
15 times faster on a CPU? That really opens up possibilities for running capable AI on, like, phones or laptops without special hardware.
That's the implication. It shows potential for resource-constrained environments. Plus, remember the training data point. Less than 2% of the training data compared to mainstream models. That just makes development so much more accessible.
It's hard to overstate how much that changes the game. Speed, efficiency, accessibility. So let's reconsider that point about the existing companies. If AI becomes this much less resource-intensive, doesn't that shrink the market for the big hardware sellers?
It's a fair question, but I think the other perspective is more likely. Lowering the barrier to entry, the cost, the power needs, doesn't necessarily mean less demand overall. It could massively increase demand.
How so?
Think of all the companies, the researchers, the applications that are currently priced out of using powerful AI. If it suddenly becomes vastly cheaper and more efficient to run, you unlock all that latent demand. You enable uses in industries and devices where it was previously impossible.
So the pie gets bigger.
Exactly. It could lead to more demand from customers who simply couldn't afford or implement the current generation of LLMs. Making AI accessible isn't just about saving money for existing users. It's about creating millions of new users and use cases. It drives that next generation of efficient and scalable large model design by opening up entirely new frontiers.
That's a really compelling way to look at it. Efficiency driving expansion, not contraction.
I think that's the real promise here.
Okay, so let's try and wrap this up. We've dived into Spiking Brain, this brain-inspired approach that tackles the massive efficiency and scaling problems of current LLMs.
Right? Using techniques like hybrid linear attention, mixture of experts, and crucially, that event-driven adaptive threshold spiking.
Which leads to incredible potential for energy savings, much better handling of long sequences, and maybe even independence from the current dominant hardware platforms.
With promising results like massive speedups and needing only a tiny fraction of the usual training data.
So, what does this all mean for you, listening right now? Well, imagine a future where really powerful AI isn't just locked away in huge data centers.
Imagine it running efficiently on your phone, in your car, maybe in tiny medical implants or environmental sensors.
A future where intelligence is embedded everywhere, quietly helping out without needing a power plant nearby. Maybe the future of AI is less about brute computational force.
And more about biological elegance, learning from the efficiency of nature.
So here's a final thought. If AI really did become, say, 100 times faster and use drastically less energy, making it accessible in ways we haven't even conceived of yet, what problem would you solve? What could you build if AI was truly everywhere?
That's definitely something worth thinking about. A lot to mull over.